lecture, we will talk about feature dimensionality reduction methods. In some classification problems, some features might represent correlated properties of the underlying class. For instance, the volume and the weight of an object. In order to get rid of the correlated features, we use feature dimensionality reduction techniques such as principal component analysis or Fisher linear discriminant. In this lecture, we introduce these methods. First of all, we will talk about principal component analysis. Here, with principal component analysis, our goal is to generate mutually uncorrelated feature dimensions in order to remove redundancies. With PCA, we project our samples along the axis of the largest variance. In order to do that, we calculate covariance matrix for the set of samples we have and find the eigenvectors that correspond to the highest eigenvalues of the covariance matrix. In this example, you can see the data scattered across the coordinate axis, and the highest variance within this scattered set of samples is in this direction. The second highest variance is in this direction. So when we calculate the principal component analysis for this data, we will find these axes. Now, with principal component analysis, we project the samples on the principal axis. For instance, suppose that this group of samples belongs to one class and this group of samples belongs to another class. When we project them in this line, we will be easily separate them by cutting the axis or cutting this line in somewhere around here. So our method with the principal component analysis, when we are given a set of features, x equals x is a member of R to the D. So we have d-dimensional samples, and suppose that we have n samples in total. We would like to find the d by d covariance matrix, that's sigma, of the training features. Second, we find the eigenvectors and the eigenvalues of the covariance matrix. And third, we sort the eigenvalues in descending order so that we can select the highest eigenvalues according to some criteria. Most of the time we will select the eigenvalues that has a high value that has much higher value than the second highest eigenvalue. So we select m eigenvalues and we also select their corresponding eigenvectors where m is less than d. This should be the case for reasonable principal component analysis, because when m is equal to d, we don't gain anything by our analysis. So then we form a transformation matrix with the eigenvectors we selected, and whenever we are given a feature xi, we transform that feature by using this transformation matrix, and while doing that we also need to subtract the mean of the samples from our given sample. So let us see how do we calculate the covariance matrix. Remember that the variance is defined as samples variance, or excuse me, the variance within a feature dimension j, that is given by this equation. So J is our feature dimension that we calculate the variance for, and n minus 1 is n is the number of samples we have. We divide the summation by n minus 1. So what do we do is we subtract the mean of the samples from each feature dimension J, and sum them up and divide by n minus 1. So for the non-diagonal elements of the covariance matrix, which is jth and kth elements of covariance matrix, we use this expression. Since covariance jk and covariance kj are the same, the covariance matrix we will have is a symmetrical matrix along the main diagonal. Next step, we calculate the eigenvalues and eigenvectors of the covariance matrix sigma, and just we need to solve the equation where we take the determinant of sigma minus I lambda and equate to 0. And this equation, this linear equation, will give us a dth degree polynomial for lambda, which will return d eigenvalues as our solution for the lambda. Having found the eigenvalues, we can calculate the eigenvectors using the equation where we multiply our matrix with an eigenvector, and that should be equal to eigenvalue multiplied by the eigenvector. Let's see an example in order to understand how we calculate covariance matrix and how we perform principal component analysis. Let us suppose that we have these samples 2.5, 2.4, 0.5, 0.7. These are our samples, and we have two feature dimensions, x to the 1 and x to the 2. First of all, we will need to calculate the means for each feature dimension. So we calculate the mean of x1, add them up, and divide by the number of samples. Similarly, for x2, we do the same thing. So after that, we will subtract the means from each feature dimension. So we subtract 1.81 from 2.5, we get this. We subtract 1.81 from 0.5, we get this, etc., etc. Then we can calculate these the entries of the covariance matrix. First of all, we will use this expression here in order to calculate the diagonal entries. So sigma 1, 1 is equal to I equals 1 from 1 to 10. This expression for each of these terms. And similarly, we calculate sigma 2, 2, and then we calculate sigma 1, 2, that's equal to sigma 2, 1 by, instead of taking the squares of taking the squares of these entries, we multiply this by this and sum them up and find the entries of the covariance matrix. After we form the covariance, by the way, I presented this in order to explain how we calculate covariance matrix by hand, but there are much better methods for programming or coding this calculation, this is one of them. However, with modern libraries like NumPy, you can use 3 or 4 lines of code, simple code for calculating this covariance matrix. Then we will need to solve the linear equation for lambda, which is the determinant of our covariance matrix minus I times lambda, that's this matrix. So we will be solving this quadratic equation, and that will give us the roots of this equation will give us the eigenvalues lambda 1 and lambda 2. In order to find the eigenvectors, we will now need to solve equation 2 for all the eigenvalues, which was equation 2. This was. So for the first eigenvector, we multiply sigma times our eigenvector, and that should be equal to lambda 1 times our eigenvector. So this is that equation, and when we solve for v1 and v2 for the components of our eigenvector, we will get these values. Similarly, for solving lambda 2, we will obtain this eigenvector. Thus, we can form our transformation matrix A with both of the eigenvectors. However, this will not be useful since it doesn't reduce the dimensionality of our data. So, we need to eliminate some of the x's. For example, in this case, we can eliminate the first eigenvector because it has a lower eigenvalue. You see this. And we have the second eigenvector as our transformation matrix. So when we decide to transform a sample, for example, we can transform second sample we have, 0.5, 0.7. We multiply our transformation matrix, transpose of transformation matrix, get our sample, subtract the mean here, and calculate its value. Also, you will need to remember that after you used to transform the training samples using the transformation matrix A, you will also need to transform the test samples using this same transformation matrix. In the last lecture, we will see Fisher discriminant analysis. See you next time.